kick things off, we'll start with first order differential equations. First, I wanted to show you guys the type of Bernoulli problem I would be asking for you to solve for the final. So that would be a question like solve the following IVP. Okay, solve the following IVP. And I won't ask you to find intervals of validity. You can skip that. I just want you guys to solve the solution, and I trust you know how to find intervals of validity very easily. So a problem could look like this. This is taken back from our notes. 6y prime minus 2y equals x y to the fourth, right? And we have an initial condition that says y of 0 equals -2. Okay, so a problem can look just like this. In fact, it looks very similar to this. And so the first thing we have to do is get the differential equation into the proper form and then write down the substitution. All right, proper form means we put all the x terms on one side and all the y terms on the other side to do Bernoulli substitution. So dividing y to the fourth to both sides, that will accomplish that task. So the next step is 6y to the minus fourth times y prime. All right, then it's going to be subtracted from 2y to the minus 3. All right, and that's going to equal x, just like this. All right, so the next question is, how do we determine what gets the substitution? Well, it's always going to be this term right there. So let me go ahead and just erase and then redirect. It's always going to be this term, okay, right next to this coefficient that you see. So this is always going to imply that this term, which in this case is v, is going to equal y to the minus 3, okay? And therefore, v prime, the first derivative of this, and by the way, we use implicit differentiation when we do these types of substitutions. So this will be minus 3 times y to the minus fourth, right? Then implicit differentiation says we need a y prime there on the right-hand side. Okay, then we plug this substitution into the differential equation, and this is going to give us minus 2v prime minus 2v, okay, equals x. And this is going to imply that v prime plus v is going to equal -1/2. It's a half times x. Okay. And this is what we have. So the way you go about solving this is by using your technique from linear differential equations, right? And so this has linear form. And so the way you go about solving that is by using the integrating factor technique, right? And so what we have here is the coefficient is a 1 here. So mu of x is going to equal e to the integral of that value, which is 1, okay? So it's just 1 times dx. Well, that's nice and easy. And so that is going to tell us that mu of x is going to be e to the x. Not too bad. And then we take that e to the x and we multiply it into the entire equation and then solve, right? So we go ahead and do that and rearrange the formulas just a bit. So we have v of x is going to equal -1/2 times x minus 1 plus c times e to the minus x. Okay, and that's after solving for the differential equation as well. So there's two things that we did. We multiplied by e to the x, isolated v prime on one side, and then integrated, okay, so that you guys know exactly what was occurring. So I'd recommend you try getting from here to here, all right? That's good review as well for you guys. You can look at your notes as well. I'll show you the steps for that. All right, so now that we're there, we can back substitute what we created for v with the y term, and this will give us the following. V of x, right? V was y to the minus 3. So that's going to equal minus 1/2, right, times x minus 1, all right, plus c e to the minus x, all right. And then we apply the initial condition to solve for c, and that's going to give us minus 1/8, which is going to equal 1/2 plus c, and this implies that c is going to equal minus 5/8, okay? It's just a matter of getting the explicit solution, but I will accept the implicit solution as well. In other words, you could just plug the c value back into here, and I would call it quits. So I would say that's fine, that's the implicit solution. But for you guys, if you want to go further, if you wanted to check intervals of validity, again, I'm going to state you don't have to do that for the final. But just for your reference, if you do solve for y and you plug in the constant, this is the solution that you get. You get 2 divided by 4x minus 4 plus 5 e to the minus x there, all raised to the 1/3 power. Okay, so that's it. That's the extent that I would expect for you to do Bernoulli differential equations and how to go about solving those. All right, so the next one for the first order differential equations involves working with concentrations, right? So that type of problem is a little more involved, but it's not too bad once you know the setup, okay? I say things like a 1,500-gallon tank, just going back over your notes. You know, we have a 1,500-gallon tank, okay? Initially contains So this initially contains 600 gallons. Okay, with 5 pounds of water dissolved in it. Okay, so this is what your notes say. Dissolved in it. Okay. There's a few other pieces of information that you need to know. So this is just the first piece. The second piece says water enters. Water enters the tank at a rate, okay, at a rate of 9 gallons per hour. Okay, and the water entering the tank has a salt concentration and the water has a salt concentration of, and they usually give you some equation. In this case, the equation was in your notes 1/5 times 1 plus the cosine of t pounds, or lbs, per gallon. Okay, and this is the second piece of information. There's one more. The third piece says if a well-mixed solution leaves the tank at a rate, all right, so this is the last piece, right? We have a well-mixed solution, and it will be a well-mixed solution in your final as well. We have a well-mixed solution. Okay, we have a well-mixed solution that leaves the tank that leaves the tank, all right, at 6 gallons per hour. Okay, so of course this is the third piece of information. So you notice there's 3 pieces of separate information that will be given to you. And the final question is, how much salt is in the tank when it overflows, right? So the final question is, with those 3 pieces of information, how much salt is in the tank right, when it overflows?